Any questions at all about the homework problems that I gave you at all? Y'all got them? What's that? No, on previous homework. Last time, the only thing I did was make a comment about the actual correct way to get the transform of that summation delay. I'm going to go through that real quick. Yes, sir.
You did post a homework problem on PTFS. Is that
discrete time Fourier series.
right?
We're going to cover that today. I just want everybody to at least think about it. That's today's, and it's very similar to the actual Fourier series problems we did, if you look at it. Now, today what I'm going to do, first thing I had down is talk about this. If I had, and I apologize for last time, not doing this correctly, but I'm going to show you something. Whenever you have something where there's some kind of a sum involved, it's an obvious recursion relationship. In this case, we had y of n equal to x of n plus x of n minus 1 plus x of n minus 2 plus dot 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 plus x of n, x of n minus, and I'm going to call this n minus 1. That would give us n terms, so n is the number of terms. All right, what that really is something that's a moving average, where it's taking the average value of a bunch of things. Technically, what this usually looks like is they divide this entire thing by n, and then what they have is the average value of a number of pulses. It's actually a low-pass filter. In Excel and things like this, they have this as a normal function. It smooths data. If you have data with some noise in it, it gets rid of it. It's a common thing. Now, the way it's usually written is this. Y of n here is equal to 1 over n, and then the summation from n equals, and really actually they have from I, typically. And it'll be from I equal 0 to n minus 1 of x of n minus I. And that should make sense to everybody. It's just the series form. The 1 over n is the scale factor that makes it the average, and then the regression, where it's just subtracting the value, progressive. And it's the average value. Remember this is a great low-pass filter for noisy data. And where this is typically used, in another book he talks a lot about this, if you ever do anything with the stock market, stock market has all sorts of nervous traders and stuff. And if you take two stocks, and I've actually had a student, we published a paper on this, we did something like what I'm about to tell you. And what we decided is, whenever a new chip comes out by the company Intel, say a Pentium chip, right, the new chip, well, we assume that's going to affect the actual sales of things that use it, like computers, laptop computers. So if you track Dell and maybe other brands that use Pentium, and you get what's called a correlation function, where you track this. We'll get to that later if I have time. We track how fast the price of Dell stock goes up when the price of Pentium stock goes up. When they introduce a new chip, people buy Pentium stock, it goes up. Then after a period of time, people buy Dell stock, and it goes up. But there's that time lag. So when people see, and this is, by the way, don't take this to the bank. I'm not sure this is true anymore. But so when people notice that Pentium stock's going up, they immediately buy Dell stock, and they put a sell order in. So as soon as that stock goes beyond the threshold, say it's normal bounds, the normal amount of increase is 20%, maybe they sell 15%. And they're going to make money. Now, this is typical trading strategies. This is the very basic thing. But they use this moving average filter on the data so they can get rid of the crazy fluctuations. They look at the general trends. Do you follow me on this, class? This is one use of this filter. And it's not electrical engineering. It's more like, what would you call that, data mining? What's that? Well, it's finance in a sense, but it really is data mining. It's an engineering, it's an application of a filtering to something that's financial. And one other thing I'll tell you, I had a kid who was really bright years ago. And this kid came out of here, and this is back in the early 90s. So salaries are about 45 to 50,000, all right? Somewhere in there for a really sharp kid. And this kid gets offered 90 grand to go to New York City and work in the finance district. They needed sharp minds. That's what they really hired. They can teach you the craft, but you've got to be bright. You've got to be good at math and programs. So they got him up there. And he called me back in about 4 or 5 years. I wish I could remember his name. He said, "Hey, can I go to grad school?" I thought you went to Wall Street. Yeah, I'm making a fortune. It's just, I hate my job. I hate everything about this place. No, really? Well, I'll try. I don't know what happened to him, but what it boiled down to, I don't know how much money he was making. No matter how much money you make, and this is another thing, if you're not happy, it doesn't matter. I mean, that's just that. Anyway, this is an application. I'm sure he used something like this. It's a long way about it. Y'all follow me on this? Let me just get the proof on this one. Now, I'm going to take the actual Fourier transform of both sides. First, I'm just going to say if we assume x of n, this is going to be the continuous time Fourier transform, goes to x of omega, then I know x of n minus anything, I can call it a, goes to simply e to the minus j a omega times x of omega. I'm not going to prove that. I'm going to assume you know that one. Are we good with that?
Yeah.
When I look at this right here, that means my y of omega, if I take the Fourier transform of both sides, is 1 over n here, and then it's going to be times the summation of, now that Fourier transform will be x of omega, right? Times e to the minus j I times omega. And here I goes from 0 to n minus 1. The only thing I've done is take the Fourier transform, the discrete time Fourier transform. Are you with me, class? This is very obvious and it's something that's important. Sorry I didn't see it. Can you see it? All right, now I'll take the x of omega out in front. So now I have y of omega here is equal to x of omega over n times this summation of really e to the minus j I omega from n equals 0 to n minus 1. And the only thing I've done there is pulled out the x of omega because it's a constant inside that sum, correct class? And now what I'll do is take x of omega by y of omega and define the transfer function. I'll say h of omega is simply equal to y of omega over x of omega. And that's equal to 1 over n here. And then it's going to be times this series. N minus 1 of e to the minus j omega times I. How many know what yeah, that's right. How many know what I'm going to do with this series right here? Isn't that really a geometric series? It's a to the n, class, right? So really here, I can say my a looks like e to the minus j omega, correct? And it's to the I power. I is like n, correct, class? And I'm summing that from 0 to n minus 1. Do y'all follow me? Give me a show of hands if you do. I'll try to write bigger. Oh, you are so far back. If you can see this, you have amazing eyes. So this is 1 over n, and then I'm going to get that to the lower power, which is just 1, minus e to the minus j, and it's this n plus 1, or just n, right? Omega, and it's divided by 1 minus e to the minus j omega. And you all remember seeing me do this several times before. Correct, class? Now I pull out the half angle business. I pull out the e to the minus j n omega over 2 up top. And in the bottom, I pull out an e to the minus j omega over 2. And you've seen me do this before. So now I get 1 over n here, and then I get e to the minus j n omega over 2 on top, and e to the minus j omega over 2 on the bottom. And then it's going to be times e to the minus, or plus j n omega over 2 here, minus e to the minus j n omega over 2 here, over e to the plus j omega over 2, minus e to the minus j omega over 2. And I know that's 1 over n, right? I'm just doing something that we've done many times. I actually put this on OneNote. I don't know if you saw it. I didn't have the 1 over n scale in there. That's all right. Now, if I take e to the minus j omega over 2 from the denominator to the numerator, it becomes e to the plus j omega over 2, right? And then when you add those things, now I get simply e to the minus j, and it would be n minus 1 omega over 2. Now, what would this turn into, guys? It's 2j times the sine of the argument, right? What does this turn into? 2j times the sine of this argument, right? How many understand that? Got to know Euler's, class. Do y'all understand this, class, please? Right? Euler's identity, you have to know those. Did you have a question?
I kind of.
Go ahead.
Okay, so you said it was 2J because of Euler's identity, right?
Well, what I'm trying to do is turn this into a sine. So I factor out this, and the reason I do is this. Euler's identity of sine theta, that's e to the j theta minus e to the minus j theta over 2j. Are you with me?
Right.
I multiply by 2j, and now I have this. So if I have e to the j theta minus e to the j theta, I've got a sine times 2j, right? That's what I'm looking for. I need the argument of this to be that. And my argument is n omega over 2. Take a look. You see it right there?
Because I was looking at the identity like earlier, and I didn't know how you got to say it.
You see what I'm doing now?
I see it now.
It's just divided by 2j, so you multiply both sides by 2j.
Right, I see it now.
All right, and for the record, what is cosine theta? Because you'll be using these all the time.
E to j theta plus e to minus j theta.
Over 2, so we can multiply that by 2 if you'd like. And then finally, this is the one, we use these three all the time. You have to know them. The next one is what? E to the j theta is equal to cosine theta plus j sine theta, right? Now those three variants on Euler's you've got to know. Got to know them. I promise you, the Jatendra Stugnate's class and the other classes you're going to,
That exponent is very rightmost in. Is that e negative j times n minus 1?
Yeah, and what I did is here, if you just watch this, all right? If this is e to the minus j n omega over 2, right? Just watch this, and you'll see. What if I take this upstairs? Doesn't this become e to the j omega over 2, right? It was e to the minus j omega over 2 down here. Upstairs, you change the sign of the exponential, right? Now, what happens when you add them together? I get e to the what? It's really minus j n omega over 2 plus j omega over 2, right? Add them together, isn't it really n minus 1 times a minus j omega over 2? You see it?
Yeah.
That's all I've done is added those things. So I have a single term. All right? And by the way, one comment about this, now I'm going to go ahead. This isn't what it equals. It's equal to this times the sine, right, of n times omega over 2 divided by the sine of omega over 2, correct? That's where I was going with this. Are you with me? And that is, this is my filter, h of omega. That is the value of this system. Now, hear me, because this is important you grasp this. When you plot this, all right, if you plot the magnitude, which you always do, forget about this term. That's a phase. That's like e to the minus j 45 degrees, something like that. It has a magnitude of 1, understand? This is where the actual magnitude oscillates. And this looks very close to a sinc function. Now the reason is for sine of small arguments, it's approximately equal to the small argument, omega over 2. And when you look at this, there's not quite a sinc function. It actually goes up, and the value here, it'll go to 2n plus 1 will be the peak value. And if this is versus omega, it'll look like this. And it'll keep decreasing. Now, this is the important part, from here to here. You all agree if this is my h of omega, by inspection, if that's the magnitude, can everybody see it's a low-pass filter because it's centered with its largest value at 0? How many see that right there? It has to be a form of a low-pass. Admittedly, we'd like to get rid of these. Now, just for the record, these sidebands, the first one here has a peak value that's 13.2 dB less than this value. And I'm not going to prove that, but it is. It's, yes, sir.
When you have the sine omega over 2 on the bottom, what happens when omega equals 0, like right in the middle?
That's when we use L'Hopital's rule, right? If you have sine x over x and you want the value at 0, you take a derivative of sine x and you get what? Cosine x, derivative of x on the bottom is 1, right? And you take cosine x equals 0 divided by 1 is 1 over 1 is 1. So sine x over x goes to 1 at 0. It's L'Hopital's rule. How many remember L'Hopital's rule? We used to call it hospital's rule, right?
The hospital.
Hospital's rule, because you were always in the hospital when you were doing that. Because you suffered from anxiety disorders. But anyway, this is what it looks like. Now the first null here is important. Here and here. These are important, so listen to me for the L'Hopital. Please listen. Where does this occur? Well, it's obvious where something goes to zero, right? The denominator here, the sine of omega over 2, is very slowly varying and it can't go to infinity. What you're looking for is the sine of this going to 0. Now, when does sine go to 0 besides at 0? Pi, right?
Pi.
So you put pi right here to figure out that point, because this is versus omega. You say omega is equal to n over 2, right? Well, let me do it this way. You would say n over 2 omega is equal to pi. Do you follow me what I'm doing here? Because I'm looking for the angle omega. Then I'd multiply by 2 and divide by n. So I would have omega is equal to 2 pi over n. And that's 2 pi over n is this value, and this is minus 2 pi over n. And this is considered the bandwidth, theoretically, of the filter. All right? Now, it's not the 3 dB bandwidth is actually from the half power points, but this is good enough to figure it out. Now, you can see if you've got a large value of n, what happens to that? If n is what? 100, that's what? 2 pi by 100. 360 degrees by 100 is 3.6 degrees. In radians, that's very small, and that will translate into a frequency, cutoff frequency that's very low. Follow me, class? There's more to this, and I'll show you how when we get into windowing, and hopefully we'll have time for this, we can reduce this side load. This is minus 13.2 dB below this height. We can actually use something called a Hamming window and bring this down to about 40 dB or more below this. 40 dB is a factor of 10,000. Does everybody understand that? At that point, it's basically non-existent. The downside of windowing, it broadens this a little, but if you have enough terms, you really don't care. You just want to get rid of all these bumps up the bump, these sidebands, you might say. Understand, class? I know it's a little bit further. Yes, sir.
What does that say the amplitude? 2n?
2n plus 1. N is the number of actual what? Samples. Isn't that right, class? Yes, sir.
Did you not need the 2J?
Where? Well, the 2J's cancel, don't they?
Okay.
If you think about this, I got sine, I got 2J on top, 2J on the bottom, they cancel.
Okay.
Yeah, they do. Yes, sir. Oh, you're not answering. All right. So that's sort of what's going on. Now, I want to tell you, remember, omega here translates to what? Small omega times the sampling frequency, right? I don't know if you remember that, but that's how we actually figured it out. So the actual frequency omega would be this, 2 pi over n, divided by ts. That would be in radians, right? And then if we divide by 2 pi, we'd have the cutoff frequency in hertz. That's how you bring it back to your actual experience with filters. Your filters have cutoff frequencies or 3 dB frequencies in hertz, don't they? I mean, how many made filters before measured them or did something with them? Come on, guys, didn't you have circuits in a circuits lab? Didn't you do low pass, high pass, band stop? Show of hands here if you've done that. Hey, there we go. Life. Well, we didn't call it that. Okay, whatever you called it, that's what I'm talking about. I mean, you had to calculate a low frequency cutoff for an RC, right? It's 1 over RC was equal to what? Tau, right? And what is tau? It's what? 1 over omega? And that's 2 pi f, right? You're looking at me like I'm speaking. I'm not.
They sort of color hands through that one.
What's that?
They sort of color hands through that one. They hit the elder.
That's the last one we did.
It'll become real to you. Look, when I had laboratories, we had stuff that they said, oh, you'll get to that in another course. And
Yeah, that's exactly what he said.
there was always stuff that there was.
Said, don't worry about the final, then get the final.
One thing I never liked about labs when I had them, we had a parts guy, and you have to go and get parts from him. And you had to return them. The thing is, nobody ever checked the parts if they were busted when they got returned, if they were burned out or something. And, you know, it seemed inevitable that at least something very important was not working whenever we built the whole thing if we didn't test all the parts. You'll learn very soon before you actually construct something, make sure every part is what it says it is. And that takes a lot of time. All right, that's one thing I want to cover. Next thing I want to cover, and that's important what I'm showing you here. This is the DFT. Now pay attention to this. I'm going to warn you about something. Reading the book sometimes can confuse you on some of these. I'm going to do it the way I would want it shown to me if I was where you're at. So this is called the DFT. It's discrete Fourier transform. All right? The DFT is simply, and I'll show you how it's developed from the DTFT. Remember the DTFT is this. It says x of omega is equal to a summation, and here we go from minus infinity to infinity of x of n times e to the minus j n capital omega, right? Now, that has, the series extent is infinite, correct, class? Now, the first assumption is now we're going to apply this to something that is actually real and observable. That means there's going to be a finite amount of data. Follow me? The points now don't have an infinite number of points. We're going to cut that down. So the first thing we do is we take this, and now we trim it in terms of the number of points. So instead of from minus infinity to infinity, it's going to go from 0 to n minus 1. Capital N would be the number of samples that we have available to us. Now the next thing, and by the way, this is still technically this, it's just what? If we're starting at minus infinity, it's a waste of time because all the values of x of n are 0 technically, right? If they don't have a non-zero value, it's an assumed 0. So then we have x of n times e to the minus j, and here's the point. Now that omega you know is what? It can go from 0 to 2 pi, and after that it just repeats itself, doesn't it? Y'all follow me, class? Think about this. Didn't we say from minus pi to pi, you're going to get a transform? And if we just took a picture of that and moved it from pi to 3 pi, it would replicate every 2 pi. Follow me on this? Now, what happens with the DTFT is we have a finite number of samples in time. It means we will have a finite number of frequency components available. The smallest frequency increment will be equal to, and write this down, it will be 2 pi over n, and that should make sense. If I have 100 points, remember my total frequency range always goes from minus pi to pi over a range of 2 pi. Follow me? So I have 2 pi as my total frequency range, so I divide it up by the number of samples, and that will be the frequency increment. Does this make sense to people? I can do this a little different way, but I think it would be more confusing. Now, this is taken to the nth power, right? But that's just the frequency increment. I have to put a value k here. Now 2 pi k n is like omega, and I'm going to show you. You can think omega sub k is 2 pi over n times k. What this is really, if you think about it, if you have 0 radians here, that would be equal to 2 pi over n times 0, or k would be 0, right? Now, if you had, say, 2 pi over n radians, that would correspond to 2 pi k, or 2 pi n times 1, where k would be 1. Do you follow me? And what this is k increases, the index of k increases, you're increasing in the frequency range. Do you follow me on this, class? That's the only thing. The k is like an index. The 2 pi over n is the delta of capital omega. It's the change, the smallest possible change. You start at 0, then you go to delta of omega, then 2 delta of omega, and so forth. Now, this right here is called the DTFT, but in our book they do it slightly different. This is the standard way. What they do is they normalize this. They take this 1 over n right there, just put that there, and they call this x of k. Please write this down. Now that is the equivalent of this for a finite series of points. Only it's scaled by 1 over n. That's the one difference. Just go with me on this. Now, when you had this, do you remember how, from this one, how you actually got x of n? If you knew x of omega, what I've shown you here is called what? That's analysis of a signal, correct? For synthesis, we know what? X of small n is equal to 1 over 2 pi. That's the frequency range extent, right, from 0 to 2 pi, times the integral from minus pi to pi of x of capital omega times e to the j n omega d omega. Isn't it, class? That's the definition. That's synthesis. And the reason they call it about that like that is because if I create a filter where x of omega is h of omega, then when I take a look at that, when I do the inverse on that, I get the impulse response, don't I? And that's important. And we don't want non-causal impulses responses if we're going to do any kind of real-time data process. So now I look over here, and I need to know, how do I get x of n here? Well, my x of n here will be equal to the summation here, and then it'll be from not n, but now it will be from k equals 0 to n minus 1, and it will be of capital X of k times e to the minus j, or plus j 2 pi over n, and then it would be to the nk. And I'm going to make one other comment. Now please listen to this. Many books in many places, what they do is they don't put the 1 over n here. Do you follow me? What they'll do is put the 1 over n here. It's essentially the same thing, all right? They'll just take the 1 over n scale factor and they'll move it over to the other one for synthesis. Do you understand that, class? But don't get hung up with this. This is the one we'll use because the book uses it. So that is the DT, or the DFT, right here. I'm going to do an example, and I've got to show you something about the bracketed notation the book uses also. Try to understand. This can seem overwhelming, but it's not. You have to spend time with it, but you'll absorb it all, and once you see how they all connect, then a light bulb goes off and it makes sense, and you feel a peace come off your chest, if you can believe that. Once you see how it all connects, and it'll make sense, especially if you're designing stuff. So now what I'm going to do is just do this for a couple of them, and I'm going to show you something called curly bracket notation. I mentioned this to you before when we did convolution in discrete time. If you have a function x, what they often do is just give singular values for it for a number of points. So they'll have something like this. They're going to put a curly bracket here. That simply means this is a finite number of points. And they may have something like 1, say 2, 1, and minus 1 here. That's 4 points. So then you put over here the number of points is 4, right? And then what they'll do is they'll underline or put an underscore where the 0 is. So here, if I did that, it assumes that n equals 0 is associated with 2. This would be minus 1 would be n, this would be 1, and this would be 2. And these are values of n. You follow me on that? Just think about what I'm doing. Now that curly bracket notation makes sense. It basically says if we have a finite number of data points, I'll underline the one where n is 0, and those are the values. Now, if we were going to do the DTF or the DFT on this, we're going to do it just so you see it done. And it's straightforward. I first write out what it is. X of k is equal to the summation, right? N equals 0. How many points? 4. So it'd be 4 minus 1 or 3, right? N minus 1. And then I'd put x of n here times e to the minus j, and then it's going to be 2 pi over 4 or pi over 2, right? And that is to the nk power. You all see that? I've taken omega, the omega there, or I should say the delta omega, would be equal to 2 pi over 4 because there are 4 points. Follow me on this, guys? Can you see it okay?
I'm trying to see that pi over 2.
This is pi over 2 because the way I got pi over 2, I said this is 2 pi over n. Since n is 4, it's pi over 2. I'll try to write bigger. Can you all see it back there? Now, when I look at this right here, that's really what? 1 at an angle of minus 90 degrees, isn't it, class? Or minus j. All right. Now, let's just take this. What is x of k equals 0 going to be? Oh, I'm sorry. I forgot the 1 over 4 here. Sorry, it's a scale factor. So, what's the first value going to be? Well, I'll give you a tip. What is the value of k here? It's 0, right? X of k is 0. When it's 0, what is this term? 1. So what are we really doing? Adding up the values and dividing by
5, 1, and 4.
Yeah, and actually, I'll tell you back, take it back. For this one, I did something wrong here. This doesn't start at 0, it starts at -1, my bad. So this actually starts at -1. I gotta tell you one other thing about this. This is over the range, and if it starts at -1 here, then you've got to reduce this, it would be n-2 up here. Follow me? It's always over the range where the non-zero values exist. My bad on that one. So take a look at this. This is -1 to 3, correct? I'm starting at -1.
Should be minus 1 to 2.
Yeah, you're right. Absolutely right. Whoever said that is right. Now, what I'm going to do first, though, is get x of 0. All right? And capital X of 0, that's still equal to 1/4, right? That's 1, right? So what are we doing? We're just adding up all the values in those curly brackets. Yeah.
Why is K on the outside of the power instead of on the original?
It doesn't matter where it is, you know? Isn't this thing, if I have, let me show you this. If I have e to the k to the nth power, isn't that e to the k n?
Oh, yeah.
It doesn't matter where it is. Put it wherever you want. But nevertheless, when k is 0, this is 1, right? So I'm adding them all up. And if I do, I have 1 minus 1 is 0, and then I have 1 plus 2 is 3. So it would be times 3 or 3/4. Now, what is x of 1 equal to? Well, that's 1/4, right? Now work with me on this one. This is x of 1. Listen to me, right? Here, when this is 1, it means k is 1, correct? So now really what I have is this. I'm going to have the summation from n equals -1 to 2 of x of n, and I'll put it in a second, times e to the minus j pi over 2 times n. That's what I'm after, right? I have 1/4 as a scale, and now I'm summing these. K is 1, so this is what I have, correct? Just watch me on this one, please. Okay? What is this going to be? That's going to be 1/4, right? Do the first value. When n is -1, x is 1, right? You all see this? All right, so I'm just putting in the value of x and n for -1 is 1. And what's this value going to be?
J.
E to the plus j pi over 2, right? Because n is -1. And that's going to be, I'm going to leave it as e to the j pi over 2. You're right, it is in fact j. But I'm going to leave it this way for a second, all right? What's the next term? Plus, keep going. N is equal to 0 now, correct, class? What is x of 0? Take a look. 2, right? And it's going to be multiplied by e to the minus j pi over 2 times 0. What is that? 1, so it's plus 2. Go to the next value. N equal 1, right? N equal 1, x of n is 1. That goes here. Now it's going to be e to the minus j pi over 2 times 1, right? Plus e to the minus j pi over 2. Keep going. What's the next value? Now x of n, that's at 2, right? N equal 2, correct, class? That's -1, so -1 goes in here, right? I can actually write this down. It would be -1, right? Then it would be e to the minus j what?
Pi over 2.
Just pi, right? It's pi over 2 times 2 or pi, correct, class? Show of hands here, see this, you see this. Y'all see this? Now you have to think about this mechanically. What really is happening is what? This is like something where I have e at a j theta, like a hand of a clock, and I start winding it, don't I? What I've really got is this thing that's winding around. That's all it is. It's going in 90-degree increments. Every time I'm summing this way, and I'm multiplying it by the actual value. What is this value going to be? Well, look at, what is this plus this? Y'all see that's what? That's j and that's minus j, isn't it? It's 0. What happens here? We have 2, right? And what is e to the minus j pi, class?
-1.
Minus 1 with a minus is plus 1. 2 plus 1 is 3 divided by 4 is 3/4, correct? I'll do one more. What is x of 2 going to be? By now you're getting it. Where do I start? N equals -1, right? Right? But remember, k is 2. So now this is really e to the minus j pi, right? Times n, correct? So when n is equal to -1, it's e to the j pi, isn't it, class? What's wrong?
What is K?
What?
We can't figure out what K is.
K is this index right here, right? When you have the frequency index right here, you have 2 pi n, right? That's the delta omega, right? When it's multiplied by k, that's like incrementing in frequency. K equals 0 is DC. K equals 1 is the lowest frequency, would be 2 pi over n, or pi over 2, right? K equals 2. It's just like, instead of having a continuum of omega, we have a discrete values of omega. So now we index those discrete values with k. Does that make sense?
So N is not the number of values.
N is the number of points, right? Right, small n? Or n is a point. Capital N is the number of points, but there's the same number of frequency points as there are time or n points in time, all right? Let me just finish this right here. So what is this one going to be, guys? Think about this. When I have k equals 2, I have e to the minus j pi, right? To the nth power, right? E to the minus j pi, all right, to the nth power. Well, what is e to the minus j? What is e to the plus or minus j pi in one word? -1, right? So here we have -1, right? And we are at n equals, I'm not going to get the answers I want. Let's do it again. I can say that this is going to be e to the minus j what? N pi, right? Because k is 2, correct, class? Now, when n is -1, what is this?
E to the j pi.
Thank you. E to the j pi. Keep going. It's going to be times 1, right? Plus 2, right? Because 2 is at n equals 0, so you don't have any kind of an angle there, always, right? What's the next one? It's going to be plus e to the minus j pi. Now, if you look at this, right, when n is equal to 1, it's minus j pi, right? What about 2? Then it's going to be -1 is the value, correct? And it's going to be e to the minus j, say it?
2 pi.
2 pi. All right, what's that equal to? I know I have 1/4. Come on, guys. What? Well, what is this? What? What is e to the j pi? Come on.
1. E -1.
-1, right? E to the plus or minus 180 degrees is -1. -1, what is this? -1, right? Right? E to the minus j pi is -1 is also, right? Minus and minus is going to be -2. Plus 2 is 0. So I'm left with this. What is this?
0.
What is e to the minus j2 pi or e to the plus j2 pi?
0.
1. Right? Times 1, right? Or -1. So this is -1/4. I'll stop there. I know you want your quiz. You all see what I'm doing here? Now, I didn't have time, but I'm going to relate this to the continuous time Fourier transform. You're going to see some stuff shortly. Do me a favor, spread out. And where is my grader? Is he here? He's going to be out of the job.